Hello, dear students. Welcome to software engineering classes. Today's topic is structured design methodology through DFD or data flow diagram. First of all, we will look about structured design methodology. That is, in short, we can say SDM. So, SDM views software as a transformation function that converts given input to the desired outputs. The focus of SDM is the transformation function. It uses functional abstraction and functional decomposition. The goal of any SDM is to specify functional modules and connections. However, low coupling and high cohesion is the objective of structure design methodology. So as per this diagram, you can see some inputs are there and some expected outputs are there. While converting these input to this output, we can say some transformation functions will be applied. So on the basis of these transformation functions, we can get desired output by passing some inputs. There are four major steps in this strategy of structure design methodology. First of all, draw a DFD of the system. Second, identify most abstract inputs and most abstract outputs. Third, first level factoring. And finally, factoring of input, output, and transform modules. So first, have a look on DFD. SDM starts with a data flow diagram to capture flow of data in the proposed system. Data flow diagram provides a high level view of any system. DFD emphasizes the flow of data through the system. It ignores procedural aspects. Actually, the purpose here is different from DFDs used in requirements analysis, but notation is the same. However, there is a fundamental difference between the DFDs drawn during requirement analysis and those drawn during structure design. It is notable to mention over here that in the requirement analysis, a DFD is drawn to model the problem domain. The analyst has little control over the problem, and hence his or her task is to extract from the problem all the information and then represent it as a DFD. The DFD during design presents how the data will flow in the system when it is built. In this modeling, the major transforms or functions in the software are decided, and the DFD shows the major transforms that the software will have and how the data will flow through different transforms. To draw any data flow diagram, the following points should be taken care. Like, it starts with identifying the inputs and outputs. It work your way from inputs to output or vice versa. Additionally, if you stuck, then reverse the direction and ask that what transformations will convert to inputs and output. So by this following this practices, you will get your answer and you can proceed either through input to the output or vice versa. Never try to show control logic. If thinking about loops, if then else, start again. Label each arrow carefully. Make use of asterisk and plus notation and show sufficient details while drawing data flow diagrams. Ignore minor functions in the start that can be mentioned at later stages. For complex system, it is better to make DFD hierarchically. Now consider this example. This is an example of simple automation teller machine, or simply we can say ATM, that allows customer to withdraw money. A DFD for this ATM is shown in following figure. So you can see 7 processes are there, like starting from we can say left to right. Then we are having get dollar amount, get account number and code, validate, debit account, retrieve account record, record transaction, and update account. So these are the 7 processes that are being expected to have any ATM processes. At while one particular module is going to connect another module, on the arrow we are having some labels as well. For example, from get dollar amount to debit account, we are having amount. From get account number and code to validate, we can mention label as account number, code, likewise. This is another example, like a DFD for counting numbers of words of any program. So you can see we can pass some input, and then 4 different processes are there as get word list, sort the list, count the number of different words, and finally print the total count. Here you can see WL, that is simply word list, and SWL, we can say sorted word list. So these are 4 processes. Each and every process, or both the processes while communicating, may have different kind of labels, as we can see in this figure. Now the step 2, identifying the most abstract input or most abstract output in data elements. Most abstract input is also known as MAI, and most abstract output is also known as MAO. So let's have a look. Most systems have some basic transformation that perform the required operations. In most cases, the transformation cannot be easily applied to the actual physical input and produce the desired physical output. Instead, the input is first converted into a form on which the transformation can be applied with ease. Similarly, the main transformation modules often produce outputs that have to be converted into the desired physical output. The goal of this second step is to separate the transform in the DFD that converts the input or output to the desired format from the ones that perform the actual transformation. For this separation, once the DFD is ready, the next step is to identify the highest abstract level of input and output. Most abstract input, or MAI, this is what? This is the data elements in DFD that are furthest form of the actual inputs, but can still be considered as input to the system. These are often the data elements obtained after operations like error checking, data validation, proper formatting, and conversion are completed. Now look on most abstract outputs, or MAO. It is starting from the outputs in the data flow diagram and traveling towards the inputs. These are the data elements that are most removed from the actual outputs but can still be considered outgoing. It represents a value judgment, but choice is often obvious. Bubbles between my and Mao, central transformations. These transforms perform the basic transformation. Problem view. Each system does some inputs, output, and some processing. In many systems, the input output processing forms the large part of the code. This approach separates the different functions as subsystem primarily performing inputs, subsystem performing transformation, subsystem primarily performing output presentations. So 3 categories may be there: input, transformation, and output presentation. Now look at the same example that we have discussed earlier, counting the number of different words in a file. So this diagram will represent identification of most abstract input and most abstract output. The diagram is absolutely the same. However, you can see Some additional points are mentioned over here, like my and mau. Look at this dotted line. My simply means most abstract input. That means after this line, no input will be there. Or in other words, we can say before this dotted line, all are the inputs. That means get word list and sort the list. These two processes may be considered as input. While after this particular dotted line, which is mentioned over here, my, no input will be there. After that, some transformation may be there, some output may be there. Okay, but after this dotted line, no input will be there. Now look at this particular dotted line that is mentioned over here, mau, most abstract output. After this particular dotted line, only output processes will be there. So we can see only one process is there, like print the count. So this is what? This is our output. However, importantly, in between both the dotted lines, or we can say in between my and mau, there must be at least one inner process. That inner process will be known as transformation. Here we can say the transformation is what? Count the number of different words. This particular process is neither input nor output. So that's why it is considered in between my and mau. So this is the logic of identifying my and mau, most abstract input and most abstract output in any DFD. Now look at the second example, that was of ATM. So example is diagram is absolutely the same. We are having 7 different processes. Now look at these dotted line, this particular line. It says what? This is my most abstract input, which means before this particular line, all the processes will be considered as input to the system. And after this particular line, some transformation processes will be there. So in this case, when we consider this particular line as my, so before this dotted line, we can have 3 different processes like get dollar amount, get account number and code, and validate. All these processes will be considered as input. Whereas after this dotted line, some processes may be considered as transformation or some may be considered as output. But to differentiate between intermediate processes or transformation processes to and output processes, we must have to find it out most abstract output, which is this particular dotted line. This line says after this particular line, all the processes will be considered as output. So we can see 2 processes are there as record transaction and update account. These 2 processes will be considered as output. However, in between these 2 dotted line, my and mau, we can have 2 different processes or inner processes, or we can say transformation. These processes are debit account and retrieve account record. So by doing so, we can categorize our DFD into 3 parts: input, transformation, and output. While designing such type of SDM or DFD, you must take care that at least one process should be there in case of input, at least one process should be in transformation state, and at least one process must be of at output stage. So this is the idea of my and mau. Now look at the first level factoring. First step towards a structure chart, it is first level factoring. It specify a main module. For each most abstract input data item, specify a subordinate input module. The purpose of these input modules is to deliver to main the MAI data items. For each most abstract output data element, specify an output module. For each central transform, specify a subroutine transform module as well. Inputs and outputs of these transform modules are specified in the DFD. First level factoring is straightforward in nature. Main module is a coordinate module. Some subordinates are responsible for delivering the logical inputs. These are passed to transform modules to get them converted to logical output as well. Output modules then consume them. Each of three different types of modules can be designed separately, and these modules are independent. Now look at this example. This is the first level factoring for sorting the list. So as you can see, there is a one module like main module. So all the processes are being attached with this main module as get sorted word list, count number of different words, and output count. And we are having labeling from connecting from one module to another module as main and get sorted word list. We are having a data control as sorted word list. How can I say this is data control? Because at the end of this arrow, empty circle is there. If the circle is filled, then we can say it is a control flow. This is the example for ATM. Once again, you can say the first level factoring as main module is there, and all the rest of the modules are connected with this particular module, main module, as get account number, get dollar amount, retrieve account record, debit account, update account, and record transactions. So all these processes are connected with main module. And as usual, we are having some label at each and every interconnection. Now look at factoring input modules. The transform that produce the main data is treated as a central transform. Then repeat the process of first level factoring. Input module being factored become the main module. A subordinate input module is created for each data item coming in this new central transform. A subordinate module is created for the new central transform. Generally, there will be no output module while factoring input modules. The new input modules are factored similarly till the physical inputs are reached. Factoring of output module is symmetrical in that case. Subordinates are transform and output modules, and usually no input modules in that case. So just have a look. We are going to factoring input modules. So input was like get sorted list. However, it can be categorized as get word list first of all and sorting of them. Get word list may be further categorized as get a word and add to word list because there may be several words in that list. So that's why we are having a loop over here till the end of the file. That will be that we can find out the word and we can add the particular word in a list. So by this way, we can get sorted list. Now focus on factoring central transforms. Factoring input output modules is straightforward if the DFD is detailed. No rules for factoring the transform modules. Top down refinement process can be used. The ultimate goal is to determine sub-transforms that will together compose the transform. Then repeat the process for newly found transforms. Treat this transform as a problem in its own right. Draw a data flow diagram. Then repeat the process of factoring. Repeat this till atomic modules are identified. So look at this diagram. This is for central transformation. In this our case, our central transformation was count number of different words. However, this can be categorized as get a word, same as previous, or increment count. However, this increment count is decisional. This is a decision call because a diamond shape is there. So if condition true, only then it will be invoked. Otherwise, one can you can see that there is a loop over here. So that means all these sub modules will be covered in this particular loop, and this is a repetitive call. So by this way, we can factor central transformation as well. So this is all about for today's lecture. For preparing this lecture, I have taken references from these four renowned books. This is all from my side for today. Thank you.